Welcome back. In this video, we're going to look at how to find the net electric field of a rod that does not have a uniform charge density. Okay? So in the last video, we looked at how to find the electric field at the origin produced by a rod with uniform charge distribution, and it had a uniform charge density. In fact, in this video, our charge density depends on x. Okay, so here's our charge density. Lambda, our linear charge density, is equal to 1/9 times the natural log of x, and it's in units of nanocoulombs per meter. Okay, now one thing I'll do is I'll say that it's in nanocoulombs per meter for two reasons. Number one, what we're going to find is that it's a pretty common thing for charge densities to be in nanocoulombs per meter. So number one, it's just common. But also number two, it's going to make the math work out very easily. Okay, and there's a reason for that, and we'll see why in just a minute. Note that there are 10 to the 9th nanocoulombs in 1 coulomb. And we're actually going to use that to convert this particular lambda into coulombs per meter. Okay, so what I can say is that this lambda, 1/9 natural log of x nanocoulombs per meter, that's equivalent to 1/9 times 10 to the minus 9th natural log of x, but now it's in units of coulombs per meter. And the reason I want it in coulombs per meter is when I apply the electric field formula, my coulombs constant k is in units of Newton meter squared per coulomb squared. So if I have coulombs squared in the denominator there, I want coulombs here to partially cancel that. I couldn't cancel a coulomb with a nanocoulomb because that just wouldn't work out. So I have to have this in coulombs per meter. Okay? So having said that, this is a non-uniform charge density, which means that if I go, let's say I pick a differential charge element dq, so this will be a differential charge element dq, okay? Then this charge that's felt at this particular point on the rod is actually different than this differential charge element right here, okay? So if you went on that point on the rod where it's red, it's actually going to feel a different charge than it would than at the blue point. So depending on the distance that a point on the rod is from the origin, there's going to be a different charge, okay? If you were to actually take x equal to 1 here, if you were to take x equal to 1 here and find out what the charge density is there, you'd find it has no charge density. Because if you take x equal to 1 here and plug it into the charge density formula, you'd have the natural log of 1, which is 0. So there's actually no charge density here at x equals 1. But you can see that as you move along this rod from left to right, as you approach x equal to 2, you should have a higher charge density. Okay? And the reason you have a higher charge density is because your x value is increasing. Okay? Your x value is increasing. At x equals 2, this is going to be a higher number than at x equals 1. At x equals 1, the charge density is equal to 0. At x equal 2, it's some number greater than that. I don't want to compute what natural log of 2 is. It's not a nice number. But suffice it to say, you're going to have a higher charge density over here on the right side than you would at x equal to 1. But the whole idea here is that the charge density is not uniform. But we're going to have to, in any case, find an expression for dq. In the last video, we showed that the differential charge element dq is essentially equal to lambda times dx. And you can go back to the last video and you can see how we proved that. But when you have a rod of any kind in a problem like this is always the formula you want to go to, that dq is equal to lambda times dx. So we're going to say that our differential charge element dq is going to be equal to, well, we converted this to coulombs per meter, so this is 1/9 times 10 to the minus 9th, and that's multiplied times the natural log of x, and then we multiply that times dx. Okay, so that's our term for dq. Well, we know that if we have a differential electric field element, which is equal to coulombs constant times dq divided by the square of the distance between that particular point on the rod and the origin, which is normally r squared, but since we're on the x-axis, we're just going to go ahead and convert that to x squared. They're equivalent in this formula. Okay? So now let's go ahead and plug these things in. Okay, we'll say that a differential electric field element is equal to K. K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. And then we're going to multiply that times dq, but dq is 1/9 times 10 to the minus 9th, and that's multiplied times natural log of x, and we divide that by x squared and multiply by dx. So you can pretty easily see that we're going to be doing an integral. So let's do this. Let's integrate both sides. We'll integrate dE from 0 to E, and that's just going to give us the total electric field. All this stuff over here is a constant. We'll deal with it in a minute, but we're essentially going to be integrating this function, ln of x over x squared dx. And in this problem, the smallest value of x for the rod is 1, the largest value is 2, so our integral is going to be from x equals 1 to x equals 2. Notice that in the case of the constant, 10 to the 9th cancels with 10 to the minus 9th. 9 divided by 9 is 1, so that's the reason I chose these values, is so our constant out in front is just going to be 1. And so we don't have to deal with a constant, we're just dealing with the integral. So that means that our electric field, our total electric field felt at the origin, is going to be the integral from 1 to 2 of the natural log of x divided by x squared dx. What I'm going to do is I'm going to rewrite this integral so that it becomes easier to see what we're going to have to do. So it's going to be the integral from 1 to 2 of natural log of x times x to the minus second. 1 over x squared is equal to x to the minus second times dx. Okay? Now, this looks like sort of an imposing integral, okay? And the reason I expose you to this is so you're exposed to different integration techniques, okay? So if you have a polynomial of some sort and a natural log function, your best bet of trying to eliminate this integral is doing an integration by parts, and what you want to do usually is set your u equal to the natural log of x, okay? The natural log, really, of the absolute value of x. And so that means that your du is going to be equal to 1 over x dx. Okay? If you want to prove that to yourself, take the integral of du, and you get u, which is above, and take the integral of 1 over x dx. You get the natural log of the absolute value of x. Okay? So this is perfectly valid, so we basically set our u equal to natural log of x. That's this part right here. Well, what we're going to want to do now is we're going to want to set our dv. We want to set our dv equal to x to the minus second dx. So that means our dv is going to be x to the minus second dx, which makes our v equal to what? Well, if you integrate x to the minus second, you get negative 1 over x, which is equal to negative x to the minus first. And challenge yourself, take the derivative of negative x to the minus first, you should get x to the minus second, and in differential elements it's x to the minus second dx. Okay? So these are our substitutions that we're going to make. Okay? So now let's actually do the integral. Okay? And the way you do an integration by parts integral is once you have these values set, you're going to say, okay, well, I'm going to take the product of u times v. Okay? So the product of u times v in this case is negative natural log of the absolute value of x divided by x. And that's going to be evaluated from, in this case, 1 to 2. X equals 1 to x equals 2. Okay? And then you subtract off from that the integral of the same bounds of v du. Okay? Well, what's v in this case? V in this case is negative 1 over x, right? What's du? It's 1 over x dx. So this is 1 over x dx, and that's evaluated from 1 to 2. Okay, so let's clean this up a little bit. Okay, so this is going to be equal to negative natural log of x over x evaluated from 1 to 2. I'm not going to try and solve this because think about it. If you take the natural log of 1, yeah, you get 0. but natural log of 2 is some strange number. It's more worth your time to actually see how you would set up the integral, not how you calculate this. So I'm not going to solve that. But in any case, you would subtract off the integral. Well, this is the minus signs will cancel to a positive, so this is going to be plus the integral, and this is going to be 1 over x squared dx. Okay. Well, let's clean this up even more. Let's put it in a form that's pretty easy to integrate. I get this is equal to the negative natural log of x over x, evaluated from 1 to 2. Well, what's the integral of 1 over x squared? Well, the integral of 1 over x squared, remember, this is just the integral of, this is the integral, let me undo that. This is the integral of x to the negative second dx. Well, we actually already solved what that was. It's negative 1 over x. So this is going to be subtracting 1 over x, and that's going to be evaluated from 1 to 2. So I need to put my limits of integration here, evaluated from 1 to 2. Okay, and you could go ahead and solve what this is. Okay, it's not really that difficult to evaluate negative 1 over x from 1 to 2, but as you can plainly see, it's not going to be nice to evaluate natural log of 2. So I'm just going to leave it like this as an absolute answer. Okay, if you had a calculator, you could solve this integral for an exact number. If you don't have a calculator, then you can't solve this. And in a lot of cases, like at the school that I'm at, they don't give you calculators, and so you can't evaluate this absolutely. But this is an absolute answer. This is absolutely correct, so I'm going to leave it like this. So our electric field that's felt at the origin due to a non-uniformly distributed charge rod is equal to this expression right here. Okay, and this is about the worst case you can get. You probably won't have to do trigonometric substitution on a problem like this. In general, what it's going to boil down to is probably U substitution, power rule, and then you could probably also have like this, integration by parts. But that's about all you should have on this. You shouldn't have anything like partial fraction decomposition or trig sub. So I hope this video gave you a little bit of intuition on how to compute these integrals. See you in the next video.